Welcome back. In this video, we're covering section 8.2 in OpenIntro statistics, fitting a line by least squares regression. We'll figure out what makes a line the best line, look at the conditions that need to hold up for that line to be trustworthy, calculate the slope and intercept by hand, and then interpret and use the model, including the dangers of extrapolation, even though we covered that a little bit in the previous lecture. When we fit a line to the data, we want one with small residuals. But how do we combine every residual into a single number? So option one is minimize the sum of the absolute values of the residuals. Option two is minimize the sum of the squared residuals. This is called least squares, and it's the approach that statisticians almost always use. Why least squares? First, it's simply the most commonly used method. But second, it's easier to compute both by hands and with software. And third, in many applications, a residual twice as large as a number is usually more than twice as bad. And when we square the residuals, it captures that. The least squares line is written y hat equals beta 0 plus beta 1 times x. Keep that notation straight. We use Greek letters, and sometimes we'll use alpha, beta, gamma. Other times, we use beta sub 0, beta sub 1, beta sub 2. The key is to choose one and stick with it. Because the textbook was using beta 0, beta 1, we'll use beta 0 and beta 1 in the slots. So before we trust a least squares line, three conditions should roughly hold. First, we need linearity. The relationship between x and y should actually be linear. So we can check this with a scatter plot or with a residuals plot. Second, we need nearly normal residuals. Now, this may not hold perfectly when there are unusual observations that don't follow the trend or the rest of the data, but we can check this with a histogram or normal probability plot. And third, we need constant variability, also called homoscedasticity. Basically, what that means is that the spread of residuals around 0 should stay roughly constant across the range of x, like you can see in the residuals on the plot on the right. You don't want to see some crazy variation up here at the high end or down here at the low end. Now let's work through an actual example. Say we're predicting the percent of a state's residents living in poverty from its high school graduation rate. Our sample of 51 states has a mean high school graduation rate of 86, just over 86, 86.01%, with a standard deviation of 3.73. A mean poverty rate of 11.35%, and a standard deviation of 3.1. And together, these two variables have a correlation of negative 0.75. The slope of the regression line is calculated as B1, beta sub 1, equals SY over SX times R. In context, that's 3.1 over 3.73 times negative 0.75, which gives us B1 equals negative 0.62. So for each additional percentage point in high school graduation rate, we'd expect the percent living in poverty to be lower, on average by 0.62 percentage points. The intercept is where the regression line crosses the y-axis. To find it, we use the fact that the regression line always passes through the point x bar, y bar. B0 equals y bar minus B1 times x bar. So when we plug in our numbers, 11.35 minus negative 0.62 times B6.01, which works out to 64.68. We can put the slope and the intercept together, creating a least squares line. So our least squares line here is the percent in poverty equals 64.68 minus 0.62 times the percent of high school graduates. That's the line that best fits our data using the least squares criteria. Now let's interpret these two numbers generally. So the intercept, that's when x is equal to 0, y is expected to equal the intercept. The slope, for each 1 unit increase in x, y is expected to increase or decrease on average by the slope. But one important note, these statements describe an association, not the causation, unless the data comes from a randomized control experiment. We have to be very careful when we're interpreting the results of our regression analysis that there is an association between the two variables, that we see this relationship, not that it is causal. Now, a note on extrapolation. Applying a model estimate to values outside of the range of the original data is called extrapolation, like looking at adult characteristics to estimate an infant's weight. Sometimes the intercept itself is an extrapolation. Notice here, pulling up um, this scatter plot from earlier, we had all of our data around here. There was no observations down even below 70, but we still have the intercept calculated for the line of best fit. So if we tried to use that intercept to describe the data at all, that'd be extending far beyond what our model could reliably tell us. And estimates that far from the data should not be trusted. So while our model is very good for explaining what's going on in here, if we tried to say, well, if a state had, no high school graduates, no one was able to do that, percent poverty would be up here. Would likely be different. But finally, how do we measure the overall strength of the fit? The most common measure is R squared, calculated as the square of the correlation coefficient. It tells us what percent of the variability in the response variable is explained by the model. The remainder is explained by variables not included in the model or by the inherent randomness in the data. For the model we've been working with, the R squared equals negative 0.62 squared, which is about 0.68. So that means about 38% of the variability in poverty rates across the states is explained by the high school graduation rate.